in our previous classes some of the relationships that are very basic to understand what happens when we have seasonal variation and when a free phase becomes a residual phase. This is very important stuff because it's going to base your knowledge on how you're going to work in the field, why your remediation is going to work, or maybe it's not going to work very properly. Why? That's because of this physical phenomenon that we explained in the previous classes. You learned interfacial tension that relates to fluids, and you learn wettability that relates to fluids and a surface. This is very important and you have to keep in mind. Now we're going to see how this relates when we have actually a porous medium. This is basic for what you're going to learn in this course. Okay, capillarity, as we have in the field, it's very important when you have immiscible flow. It's the most important thing. Just like you have hydraulic conductivity as the most important thing for when you have a single fluid flowing, a single fluid flowing. Now for immiscible displacement, capillarity is the important thing. Well, we have probably the most common way of watching capillarity here. Take a look. We have a tube, a glass tube, you have water, and you have air here. And we have the meniscus here. The meniscus is something that you use to see. But now we're going to show you how we have to take a closer look to understand that. Look at that. Well, now in this meniscus here, what we have here is our contact angle. And from our previous class, we know now that the contact angle is measured within the denser fluid, and that is not new for you because water is denser than air, right? So water, the contact angle is measured here. Well, so I can tell you, and you know that from the previous class, that water is the wetting fluid with respect to air. So water is the wetting fluid of the glass tube with respect to air. The sentence is correctly put when I said it again. Why? Because I used the three materials: the wetting fluid, the surface, and the non-wetting fluid. Okay? That's very important to keep in mind. Okay? Water is the wetting fluid that invades the space of the non-wetting fluid, air. Actually, when we think about capillarity and we think about capillary fringe, we see that the water invades and it moves upwards and goes invading all the pores. If you have a piece of paper and you put a droplet of water and you see that it invades the pores in all directions. Capillarity actually acts in all directions, and we see that clearly, right? Well, capillary tends to invade. The wetting fluid actually displaces, it pushes the other fluid. You remember that you cannot actually pull a fluid, you can only push a fluid, right? So capillarity is pushing the other fluids. So if you have water invading a porous medium, it is actually displacing air, if the air was the fluid that was previously filling the pore spaces. Okay, so the wetting fluid displaces the non-wetting fluid, and as it displaces, it adds some pressure to this fluid. This is very important, and you see from here. Take a look. A shape. This is a balloon. We have the external pressure in this balloon, and we have the internal pressure in this balloon. Which pressure is higher? Okay. Internal or external? And why? Well, let's think if you take a small pin and prick this balloon, boom! Why it goes like that? Because the air that is inside tends to move outside fast, right? Why? Because it's under pressure. So the internal pressure is much higher than the external. It tends to go away from where it is, right? So it should be intuitive. Internal pressure is higher. if you think of a balloon. Take a look here, internal pressure is higher. Well, we're not going to see many equations in this course. I don't want you to make it too tough on you. But this one is very important because it'll help you to understand and to think of capillarity in its own way. This is called Young's equation from its creator. Capillary pressure, interfacial tension here, IFT, interfacial tension, contact angle, and the radius of the meniscus, okay? Or the tube that is in here. Or the size of the pore, the radius of the pore that we're talking about. Well, we can clearly understand that capillary pressure is directly proportional to interfacial tension and contact angle. But let's think of a perfectly wetting fluid, like I said to you in the previous class. Water is the wetting fluid of the aquifer. So this contact angle here, if this is perfectly wetting, contact angle is going to be 0. And then this here, cosine, is going to be 1. So our equation is going to end up like 2 times interfacial tension divided by radius, because this is 1, right? In our aquifers. Well, capillary pressure will then depend mostly on the radius, because interfacial tension between the fluids tend to remain approximately constant. It doesn't change much if we consider 2 fluids that don't change their properties too much, okay? But the radius of the pores may be different. That's why we can have different elevation of capillary fringe, right? If the pores, the radius of the pores are too small, then the capillary pressure is very high and the capillary fringe tends to be higher. If you have pores that are larger here, capillary pressure is going to be lower and the capillary fringe is going to be much shorter or not as thick as the other capillary fringe for clays, let's say. Okay? This is very important to understand. So again, just put it in numbers. We have the Young's equation, very simple. Capillary pressure increases with interfacial tension and vice versa, and it decreases with the radius. Okay? Wetting fluid, then, this is a very important conclusion. The wetting fluid tends to flow through smaller pores. Why? Because capillary pressure pushes into the smaller pore. Actually, it doesn't push it. The wetting fluid tends to invade the smaller pores. This is very important. The wetting fluid is the driving force. Really, the wettability is what decides the path that the fluid is going to take. The smaller the pore, the higher the capillary force. So the wettability tends to act in the smaller pores due to capillarity, and it invades the smaller pore first. That's not quite intuitive, because when you think that you're watering your garden, for example, you think that water will flow faster through larger pores, because we have relationship with rivers where capillarity doesn't exist. But when we're talking about aquifers, the capillary pressure acts very strongly, well, then the smaller pore is the one of choice for the wetting fluid. This is very, very important. On the other hand, the non-wetting fluid would rather go through a larger pore first. Okay, that's a different path that we're going to understand. Okay, smaller first. Okay, smaller first for wetting fluid, and that's what you have to understand from this class. This is very, very important. Okay? When you think on our first slide on our very first class, when we have water table fluctuations, well, now we have to understand that when the water table rises, it goes up, the water tends to displace air or displace the free phase. Since free phase is non-wetting, it goes upwards and it displaces the wetting phase. We're going to see this into detail in our next class. Thanks.